Thank you for the introduction. Welcome everyone, my name is Liz Makeley and I'm an applications engineer with Keithley Instruments. I specialize in DMMs, DACs, and switching products, and also sensitive. But today I'll be talking about two instruments that most engineers have on their bench, DMMs and oscilloscopes. Before we get started, a quick review of what we're going to cover today. We will talk about what each tool is because we need to define what we're talking about before we can make comparisons. We'll cover a list of similarities and differences between DMMs and scopes, and then we'll go through a number of application examples, and we'll talk about which tool to use for each situation and why. So with that, we'll dive right in. Scopes and DMMs are two of the most common instruments and probably the most common when it comes to measurement instrumentation. In order to understand when you should apply each of these tools, we should start by defining what they are. Digital multimeters are instruments that can be used to make a variety of measurements, hence the name multimeter. They are a measurement-only device. They typically do not provide any kind of user-controlled sourcing, although some functions like resistance do have a current source as part of it, but it's not user-controlled. The most common functions are DC voltage, DC current, and resistance. Most modern DMMs also come with lots of other functions as well, such as AC voltage, capacitance, temperature, and others. Plus, if your DMM has built-in math functions, you may be able to program it to read data from other transducers, making your DMM a meter to measure something like strain or humidity. The other really nice thing about DMMs is they just come in a wide range of capabilities and form factors. DMMs can have all the way down to 3.5 digits to 8.5 digits, and they come in benchtop versions, handheld battery operated versions, and even high density rack style for automated systems, as we can see with our DMM 7512 there at the bottom. For the most part, DMM functionality is pretty similar regardless of the model. The main difference between one DMM and another comes down to resolution and accuracy. Some applications only require you to do basically a spot check, so it's not worth paying for the super high accuracy or high resolution because you're not really using it. But for low-level measurements or measurements where you really want that high resolution, you'll need a DMM with more digits and better accuracy. Of course, the measurement you want to take is a factor. Some basic DMMs, like the handheld kinds, might not have a dedicated function for something like temperature, where higher-end DMMs will have additional features. Programmability and usability is always a factor when purchasing any kind of equipment. We're all familiar with that handheld DMM that's got the dial to change functions, but sometimes we want a little bit more out of our DMM. So having a benchtop model that's got a big screen on it, like our graphical touchscreen multimeters, will have buffers and graphing capabilities and some data visualization, as well as the ability to be remotely controlled from a computer. So that's a DMM. What about an oscilloscope? Scopes are also measurement devices, although higher end models will have arbitrary function generators built in. Really the scope itself is measurement only. Scopes are great for visual display of signals because they're making measurements based on time rather than just a single point. I'll talk more about this later when we start to compare functionality. Scopes only make voltage measurements. If we want to make a current measurement, we have to connect a current probe that converts a current signal into a voltage signal that the scope can measure. This is different than a DMM, which actually has multiple different circuits built in to make different types of measurements. So the ammeter circuit in the DMM is different than the voltmeter. With the scope, we have to include external hardware to make that conversion. Like DMM, scopes also come in a wide variety of options. They are heavily used for diagnosis purposes, so most models are benchtop style. But there are lots of selections for handheld and portable scopes these days, including our most recent 2 Series MSO, which has an optional battery pack to make it mobile. All DMMs function pretty similarly, but scopes can have a wide range of behaviors depending on the model you get, so it's important to choose a type of scope that works best for your application. Digital storage scopes are your conventional basic scopes. They're good for capturing transient signals and other signal events. The digital phosphor scope is a more advanced version of the DSO. It uses parallel processing to increase waveform capture rates so that you're getting more detail in the signals that you're capturing. Mixed domain scopes combine the scope functionality with an RF spectrum analyzer, and mixed signal scopes combine the scope functionality with a logic analyzer. Both of these scope architectures are expanding the range of signals they can capture and evaluate from just your basic scope. And then digital sampling scopes can achieve much higher bandwidths and higher speed and measure higher speed signals than DSOs or DPOs. But the trade-off is that the digital sampling scope has a lower input voltage range. There are lots of features to consider when selecting a scope, but some of the main ones include bandwidth, waveform capture rate, sample rate, and rise time. All of these contribute to how accurately your scope is able to measure and capture the waveform. The closer you are to the limits of the scope, the more likely your signal will be attenuated and the more likely you are to miss out on critical information. And of course, you want to make sure that the scope is convenient for you and has the connection options you need, because your instrument should be easy to use if you want to get the most out of it. So now we know what each of these tools are and a bit about how we would select one to use, but we're here to talk about when to use one or the other, because a lot of times we get users that'll say, why would I need a DMM? I have a scope, or vice versa. So we need to look at how the instruments are similar and how they're different to know which one is a better choice over the other for a particular application. So both of these tools are measurement devices. Standard versions of these instruments don't provide any sourcing capability. They can be used to measure both DC and AC signals, but obviously DMMs have some limitations. They can't do everything that scopes can, but scopes can't do everything DMMs can. Otherwise, there'd be no point to having two separate tools. They're both really good for debugging circuits, which is why they are such common bench tools. And their functionality can overlap a bit. As I mentioned, some scopes can have a voltmeter utility, and newer DMMs can have built-in digitizers that gives the DMM more scope-like behavior. And I'll talk more about this in a bit. So how are they different? I really like the idea of pictures versus numbers. Scopes are picture tools. They're visual. The whole point is to show the waveform on the screen. DMMs are number tools. Their goal is to take a measurement and give you that value. And this goes along with the idea that scopes are time-based measurement tools. They're taking measurements to see how waveforms are varying in time, whereas DMMs are taking measurements in the instance of time. We want to know what that voltage is right now. We want that single value. Because of this differentiation, scopes are optimized for AC behavior. Their hardware is built to operate at much higher frequencies and to make measurements on much more complex waveforms than DMMs, which are optimized for single DC measurements. The trade-off here is that DC measurements are more accurate on DMMs than scopes, and I'll explain that more later. So let's look at some application examples so that we can see how to apply this. So DMMs are better tools for understanding component behavior and characterization, because typically when we're looking at the behavior of a device like, say, a MOSFET, we're looking to characterize how the voltage and current of that device is changing with respect to other conditions in the circuit. So a really good example is a MOSFET transfer curve or characterization curve. We might have a power supply power the gate and drain terminals of the FET, and then we can use a DMM to measure the current as the gate voltage is changed. In this case, we're not concerned about how the voltage is changing over time, but rather we're just taking discrete DC measurements at various other voltages in the circuit. The DMM is more accurate over the scope for measurements like this, which brings up a really good question. Why are DMMs more accurate? Oscilloscopes are optimized for high-speed measurements because what we want to do is visualize the waveform behavior. And to accomplish this, we have to take a series of samples of that waveform and connect them together. Now, technically, you could do this with a DMM or any measurement device that's taking more than one measurement, but the issue is the speed of it. So in order to visualize that fast, complex waveform, scopes are sampling and taking measurements at a much higher rate than a DMM would. But with any measurement, you don't get speed for free, and the trade-off for speed is always noise and accuracy. The faster that we're taking measurements, the harder it is to block out noise and get a really accurate measurement. DMMs are optimized to take precise, accurate measurements and eliminate that noise, and the trade-off for that is that they take much slower measurements. So what DMMs do is they use an integrating analog to digital converter that integrates the signal over a period of time equal to the period of the line power that's coming into the DMM. So in the United States, we have 60 hertz power. So that means that the DMM, each measurement is integrating over a period of 16.67 milliseconds. And this is great. It integrates out 60 hertz noise and gives us a much better measurement. But the problem is that each measurement then is taking 16.67 milliseconds. So if you're trying to measure a pulse that has a width less than that, it's going to be very difficult to capture that behavior with a DMM, but you can with a scope. And of course, this isn't to say that your scope is not accurate, because it definitely is. And they're getting better all the time. But if you're looking to take that single DC voltage measurement on, say, like a 1 volt source, a measurement on a medium end scope, like a 6.5 digit, might vary by 10 millivolts, but on the same measurement on, a measurement on a scope might vary by 10 millivolts, but that DMM is going to only vary by 10 microvolts. So much lower resolution there. Lots of device characterization applications require that level of accuracy. So we really need to use a DMM or a similar measurement device for this instead of the scope. Going back for a second, there are some exceptions to this rule. If what you're looking to characterize is high frequency behavior, like you might want to do with a capacitive or inductive load if you're looking at filtering behavior, or if you're looking to characterize a transient behavior in a device. We see this a lot with wide bandgap MOSFETs that are used in switching applications. It's important for us to know how quickly the MOSFET can turn on and off. And the scope is a better tool for this, again, because of the high sampling rate and it's visualizing behavior over time. So this is a really good segue into another very big application for oscilloscopes, which is debugging signals and waveform behavior. There are so many things that can go wrong in a signal. We could have excessive noise, there could be timing jitter in the signal, jitter and runt pulses, which is where the pulse doesn't reach the threshold for high or low, are big concerns for binary data transmissions. We may be concerned with understanding transient behavior in a circuit when it's turning on and off, as we were with that MOSFET. We may have a circuit that just isn't behaving as expected, and we're trying to find the source of the error. We don't know if any of these things are a factor. And so this may involve looking at inputs and outputs of different sections and comparing the two to see what's going on. But the key here is that all of these signals are varying in some way, either that because the issue is intermittent or the issue has to do with timing. So because of this, the tool of choice is the scope. Again, scopes are optimized for high speed sampling and signal visualization. Many transient behaviors occur over very short periods of time, like nano to microseconds. So we need to have that high sampling rate to even see the behavior at all. With a DMM, because of that integration, we may not even see something in the readings because it happens and settles before the DMM has completed and returned a reading. We can also have the same issue with high frequency data transmissions. A DMM just isn't fast enough to capture short, quick pulses, but the scope can. High-end scopes sometimes even come with software packages that will capture and decode common data transmissions. So you don't even have to interpret the waveform to see if there's an error. You can look at the actual converted data. In most cases, a scope is a better choice for this type of testing, but there is a way to kind of get around this if you have a scope or if you have a DMM with a digitizer. The digitizing feature in the DMM takes much faster readings than just regular DC voltage or DC current mode, so it's more scope-like in behavior. So let's talk more about this. The digitizer in the DMM is not using the integrating A to D, which is the part that's forcing us to take measurements over the period of the line power signal. That's what's making the DMM slow. So because we've eliminated that, we can now up our measurement rates. And typically with a DMM digitizer, we're looking at sampling rates in the kind of megahertz range, like 1 megahertz would be the maximum. Of course, faster measurement speed does mean a dip in the accuracy and precision of the readings compared to just DC volts. At 1 megahertz sampling rates, we're looking at more of a 4.5 digit resolution versus the 6.5 or 7.5 digits that you would get if you were using the integrating A to D. But unless you really need that exact of a reading, it's worth the trade-off to get that more scope-like visualization with our data. So here I have a bunch of screen captures taken from our DMM 7510, which is one of our graphical touchscreen models that has a built-in graph utility. So you can see that the data that we're taking with the digitizer live, kind of like you would with a scope. So the bottom left images show digitizing voltage and current to capture turn-on characteristics for a DC to DC converter. It's important to characterize transient behaviors of devices when they turn on and off because that operation is not immediate. So we want to know how long it takes for the circuit to engage. On the right side, we can see comparisons between the digitizer on the DMM 7510 and a basic scope to measure ripple voltage on that same DC to DC converter. If we look at the peak-to-peak voltage, that ripple is only about 6 millivolts. And it's hard to see that ripple on the scope when it's DC coupled. We can see it when it's AC coupled, but the accuracy isn't quite as good. So, in this case, the DMM digitizer can sometimes be a slight improvement on the scope capability, especially when those signals are low level and the frequency is pretty low, like typically in the hundreds of kilohertz or lower range. Anything above that, the scope is going to beat out the DMM in performance because the sampling rates are so much higher. So sometimes what we want is to take a DMM measurement, but for some reason that measurement isn't quite what we're expecting. A lot of times this comes in the form of what we would consider noisy measurements, or measurements that are just kind of varying a lot. So what do we do when our DMM measurements aren't working quite right? Well, we can debug them with a scope. Scopes are excellent debug tools when looking at noise or signal changes. So true story, we had a customer who was experiencing noisy measurements on their DMM, and we were able to take a scope and measure the noise that was present in their environment, which we found to be unusually high, and sometimes this can be the case for manufacturing environments. But so the scope enabled us to see how much noise there was and to look at the spectrum view of that noise to identify peak frequencies. So we were able to determine that we needed an external low-pass filter to get rid of some of that noise before we could take the measurement with the DMM to get the best measurement with that DMM. So that's a great example of a case where both tools are really necessary. What if we are looking to measure some type of AC voltage signal? Well, here you can actually use either tool. And the choice comes down to basically what's your signal that you're measuring. So most modern DMMs do have an AC voltage or current function, but they're still a DC instrument, so they typically only make RMS measurements, which is basically the DC equivalent of that AC waveform. Because of this, DMMs are best for waveforms that are sine waves or at least close to sine waves. So a lot of DMMs will have crest factor specifications, and if the waveform meets that specification, then you'll still get an accurate RMS value back. DMMs do perform very well at lower frequencies, again, typically less than a few hundred kilohertz. So if your AC waveform is under 100 kilohertz, your DMM is a pretty good tool to measure in. But if it's above that, or if it's outside that crest factor specification, this scope is the only way to go. In addition to RMS values, some DMMs do have functions to measure frequency or period, but again, we're stuck at those lower frequencies. So if you want to make a measurement outside of RMS values like peak-to-peak voltage, overshoot, rise time, any of those, the scope is the best tool for that. It'll have built-in measurement functions that'll give you that value back. And that's just something a DMM is not capable of. So as circuits increase in complexity, we often are looking to measure more things, more device terminals, more inputs and outputs, more sensors, what have you. So we're pretty used to the idea that scopes can have multiple channels. I think most scopes these days have a minimum of 2 channels, so that you can at least compare 2 signals together. But lots of scopes these days have many more channels than that. Like I think we can go up to 8, channels on one scope. So that is pretty easy to do. But traditionally, DMMs have only ever been one input, and they're taking one measurement at a time. This can be adapted a little bit if you get a DMM that has some built-in switching capability. So switch cards come in a variety of configurations, the most common being a multiplexer. This allows you to connect multiple devices or multiple measurement points in your circuit to the card, and then the DMM is controlling the relays to route the desired signal for measurement. The DMM is still only taking one measurement at one point at a time. So it's not a parallel measurement, it's still a sequential measurement. But it's much more efficient than having to stop what you're doing, unwire your DMM, connect a new device, take another measurement, and repeat the process. So if you can tolerate a little bit of delay in between the measurements, it's much more cost effective than buying multiple DMMs to measure multiple signals. So here I have the 2000 scan card that goes with our DMM 6500. It's got 10 channels in it. But if you need more than that, you'd be looking at dedicated multi-channel DMMs or data loggers. For example, our 3706A system switch and multimeter can have up to 576 two-wire channels in a single mainframe. So the choice comes down to, are the signals you're trying to measure better suited for a scope, or are they better suited for a DMM? Because you have options either way to increase your density. So hopefully I've convinced you of the merits of using a DMM or scope for your application, but there's probably a lot of you out there that really need both. Luckily, Tektronix and Keithley have a really diverse portfolio of DMMs and scopes so that you can get exactly what you need for your bench. Maybe you're making mostly DMM measurements, but you need a basic scope to do some diagnosing here and there. Or you're mainly doing really complex signals and you need a high-level advanced scope. But sometimes you need that DMM to check some values in your circuit. So either way, we've got lots of options and features for you. I wanted to highlight our DMM 6500, which is our 6.5 digit touchscreen option. It's a great starter DMM, really good accuracy for the value. It does have that built-in digitizer that can sample up to 1 megahertz for DC voltage and DC current. And then, like I said, it's part of our TTI platform, so it's got a touchscreen on it, very user-friendly interface, a built-in graph to view your data, so it makes a great benchtop instrument to use from the front panel, but also it's got built-in TSP scripting capability, so you can run custom code and GUI-based applications right on the box without the need for a controlling PC as well, so that's a really cool feature. Our highlighted scope today is the 2 series MSO. It comes in 2 or 4 channel options with up to 500 megahertz bandwidth and a 2.5 gigasample per second sampling rate. So remember how I said that scopes had higher sampling rates to measure higher frequencies? That 2.5 gigahertz beats out our 1 megahertz digitizer by a lot there. But what's really cool about the 2 series MSO is how small and portable it is. This scope is only 1.5 inches thick and it only weighs 4 pounds. And we have that optional battery pack so you can take your scope around your lab kind of like a tablet, or leave it on the bench where it really doesn't take up that much space. So it is also a touchscreen model, has a nice big screen so you can see your signals really well. It has a really user-friendly GUI to make analyzing your waveforms easier, because that's the whole point of the scope. We want to see the signal on the screen and analyze it right in front of us. So to summarize what we covered today, use a DMM for low frequency or DC measurements, especially for tests like device characterization, where you're caring about the value of the signal. They're great for general purpose use. Use scopes for high frequency or really complex signals, like the kind we would use to transfer data. Scopes also should be used for any kind of time-based or frequency-based measurements. For example, rise time, transient behavior, looking at noise frequency spectrums. They are great tools for advanced troubleshooting and debugging, and there are lots of additional features, so you can really customize your scope to fit your application. But really, if you're working in a research and design lab, or in a position where you're doing just a really wide variety of testing that may involve DC signals and may involve AC signals, the best solution is to have both. DMMs and scopes work hand in hand to provide full coverage for your testing needs. So we have a number of resources available for download as part of this webinar and on our website. I've attached data sheets for the 2 Series MSO and for the DMM 6500. We also have our XYZs of Oscilloscopes Primer, which is a kind of large document, but I think it contains excellent information on key features of a scope and how to use it properly. So if you're interested in getting the most out of your scope, I highly recommend taking a look at that. And then our last document is our digital multimeter selector guide, which gives an overview and comparison of our DMM offerings and shows you all the features of the DMMs in kind of a neat table format. And then, of course, this webinar will be available on demand, so you can always come back and revisit it too. With that, thank you all so much for attending. I hope you found it beneficial.